Very good morning, friends. So, going to start again a very important chapter, chapter number 2, end-to-end machine learning project of hands-on machine learning, Scikit, Keras, and TensorFlow, third edition. Okay, I'm going to start it.
End-to-end machine learning project. In this chapter, you will work through an example project end-to-end.
Yeah.
Pretend to be a recently hired data scientist at a real estate company. This example is fictitious. The goal is to illustrate the main steps of a machine learning project, not to learn anything about the real estate business. Here are the main steps we will walk through. 1. Look at the big picture. 2. Get the data. 3. Explore and visualize the data to gain insights. 4. Prepare the data for machine learning algorithms. 5. Select a model and train it. 6. Fine-tune your model. 7. Present your solution. 8. Launch, monitor, and maintain your system, working with real data. When you are learning about machine learning, it is best to experiment with real-world data, not artificial datasets. Fortunately, there are thousands of open datasets to choose from, ranging across all sorts of domains. Here are a few places you can look to get data. Popular open data repositories: openml.org, kaggle.com, paperswithcode.com, UC Irvine Machine Learning Repository, Amazon's AWS datasets, TensorFlow datasets, Meta Portals, dataportals.org, opendataMonitor.eu. Other pages listing many popular open data repositories: Wikipedia's list of machine learning datasets, Quora.com, the datasets subreddit. In this chapter, we'll use the California housing prices dataset from the StatLib repository. This dataset is based on data from the 1990 California census.
Yeah.
It is not exactly recent, but it has many qualities for learning, so we will pretend it is recent data. For teaching purposes, I've added a categorical attribute and removed a few features. Figure 2-1. California houses.
So you can see the California housing price in this figure. You can see the longitude. According to longitude and latitude, each place have the different median house value in USD. You can see here. Okay, now moving forward.
Look at the big picture. Welcome to the Machine Learning Housing Corporation. Your first task is to use California census data to build a model of housing prices in the state. This data includes metrics such as the population, median income, and median housing price for each block group in California. Block groups are the smallest geographical unit for which the U.S. Census Bureau publishes sample data. I will call them districts for short. Your model should learn from this data and be able to predict the median housing price in any district, given all the other metrics. Since you are a well-organized data scientist, the first thing you should do is pull out your machine learning project checklist. You can start with the one in Appendix A. It should work reasonably well for most machine learning projects, but make sure to adapt it to your needs. In this chapter, we will go through many checklist items, but we will also skip a few, either because they are self-explanatory or because they will be discussed in later chapters. Frame the problem. The first question to ask your boss is what exactly the business objective is. Probably not the end goal. How does the company expect to use and benefit from this model? Knowing the objective is important, because it will determine how you frame the problem, which algorithms you will select, which performance measure you will use to evaluate your model, and how much effort you will spend tweaking it. Your boss answers that your model's output will be fed to another machine learning system, along with many other signals too. This downstream system will determine whether it is worth investing in a given area. Getting this right is critical, as it directly affects revenue. The next question to ask your boss is what the current solution looks like. The current situation will often give you a reference for performance, as well as insights on how to solve the problem. Your boss answers that the district housing prices are currently estimated manually by experts. A team gathers up-to-date information about a district, and when they cannot get the median housing price, they estimate it using complex rules. Figure 2-2. A machine learning pipeline for real estate investments. This is costly and time-consuming.
So you can see figure 2.2, a machine learning pipeline for real estate investment. You can see here first district data is there, upstream components, then my component, your components, and district pricing, and district prices are there. Then other signals and district prices go in the investment analysis. Then investments come. Okay, this is a costly, time consuming, and their estimates are not 100. Okay, fine.
And their estimates are not great. In cases where they manage to find out the actual median housing price, they often realize that their estimates were off by more than 30%. This is why the company thinks that it would be useful to train a model to predict a district's median housing price, given other data about that district. The census data looks like a great dataset to exploit for this purpose, since it includes the median housing prices of thousands of districts, as well as other data. Pipelines. A sequence of data processing components is called a data pipeline. Pipelines are very common in machine learning systems, since there is a lot of data to manipulate and many data transformations to apply.
Yeah.
Components typically run asynchronously. Each component pulls in a large amount of data, processes it, and spits out the result in another data store. Then, sometime later, The next component in the pipeline pulls in this data and spits out its own output. Each component is fairly self-contained. The interface between components is simply the data store. This makes the system simple to grasp, and different teams can focus on different components. Moreover, if a component breaks down, the downstream components can often continue to run normally by just using the last output from the broken component.
That's good.
This makes the architecture quite robust. On the other, a broken component can go unnoticed for some time if proper monitoring is not implemented. The data gets stale, and the overall system's performance drops.
Yeah.
With all this information, you are now ready to start designing your system. First, determine what kind of training supervision the model will need. Is it a supervised, unsupervised, semi-supervised, self-supervised, or reinforcement learning task? And is it a classification task, a regression task, or something else?
Yeah.
Should you use batch learning or online learning techniques? Before you read on, pause and try to answer these questions for yourself. Have you found the answers? This is clearly a typical supervised learning task, since the model can be labeled examples. It is a typical regression task, since the model will be asked to predict a value. More specifically, this is a multiple regression problem, since the system will use multiple features to make a prediction. It is also a univariate regression problem, since we are only trying to predict a single value for each district. If we were trying to predict multiple values per district, it would be a multivariate regression problem. Finally, there is no continuous flow of data coming into the system. There's no particular need to adjust to changing data rapidly, and the data is small enough to fit in memory, so plain batch learning should do just fine. If the data were huge, you could either split your batch learning work across multiple servers or use an online learning technique. Select a performance measure. Your next step is to select a performance measure. A typical performance measure for regression problems is the root mean square error. It gives an idea of how much error the system typically makes in its predictions, with a higher weight given to large errors. Equation 2-to-1 shows the mathematical formula to compute the RMSE. Equation 2-to-1. Root means square error. Notations.
Here you can see the root mean square error. The formula RMSE xh is equal to whole root of 1 by m, and then the summation of from I equal to 1 to m h xi minus yi whole square. Okay, you can see this. This is very important equation. Now starting from this notation, so this equation this equation introduce several very common machine learning notation that I will use throughout this book. Okay.
This equation introduces several very common machine learning notations that I will use throughout this book. M is the number of instances in the dataset you are measuring the RMSE. For example, if you are evaluating the RMSE on a validation set of 2,000 districts, then M equal to 20.
2000, yeah.
X is the values of the ith instance in the dataset, and Y is its label. For example, if the first dataset is located at longitude minus 118.91 degree, latitude 33.91 degree, and 416 inhabitants, with a median house value is 156.
You can see here that, for example, if the first district in the data set is located longitude is given from the graph, from that figure, minus 118.29 degree, and latitude 33.91 degree. Okay, and it has 1,416 inhabitants with median income of $38,372, and the median house value is, then we can calculate the median house value by putting the values here, $1,56,400, ignoring other features of for now. Then you can see x1 is all things written in bracket, the vector xi, the x1, okay, or the first instance in the data set. This is given here, minus 118.29, the longitude 33.91, the latitude 1,416 inhabitants, and income 38,372. Okay, and then you can see y1. Okay, y1 is the final. Okay, this is average median. Okay, that is 1,56,400. Okay, X is the matrix containing all the features, values, excluding levels of all instances in the dataset.
For instance, and the ith row is equal to the transpose of X. Noted. For example, first district is as just described. Then the matrix X looks like this. H is your system's prediction function, also called a hypothesis.
And you can see here H. Yeah, not H. In that. Okay. One minute. I think I am more upper side. Okay, here you can see H. So what is H here? HXI. The H is your system's prediction function, also called hypothesis.
When your system is given an instance's feature vector X, it outputs a predicted value equal to H for that instance. For example, if your system predicts that the median housing price in the first district is $158,400, then h equal to 158,400. The prediction error for this district is y, equal to 2000. RMSE is the cost function measured on the set of examples using your hypothesis h. We use lowercase italic font for scalar values, and function names, lowercase bold font for vectors, and uppercase bold font for matrices. Although the RMSE is generally the preferred performance measure for regression, tasks, in some contexts you may prefer to use another function. For example, if there are many outlier districts, in that case you may consider using the mean absolute error, shown in equation 2-2. Equation 2-2. Mean absolute error.
Yeah.
Both the RMSE and the MAE are
so
ways...
you can see the mean absolute error, MAE xh is equal to 1 by m, root of, the summation from I1 to m, hxi minus yi. You can see here. So both RMSE and MAE are ways to measure distance between two vectors. Okay, the vector of prediction and the vector of target values. Okay.
To measure the distance between two vectors, the vector of predictions and the vector of target values.
Okay.
Various distance measures, or norms, are possible. Computing the root of a sum of squares corresponds to the Euclidean norm. This is the notion of distance we are all familiar with. It is also called the norm, noted Aurora 2. Computing the sum of absolutes corresponds to the L, norm, noted Or. Or this is sometimes called the Manhattan norm, because it measures the distance between 2 points in a city if you can only travel along orthogonal city blocks.
Nice.
More generally, the L norm of a vector v containing n elements is defined as or 1 equal to the plus. Plus or v gives the number of non-zero elements in the vector, and L gives the maximum absolute value in the vector. The higher the norm index, the more it focuses on large values and neglects small ones. This is why the RMSE is more sensitive to outliers than the MAE. But when outliers are exponentially rare, the RMSE performs very well and is generally preferred. Check the assumptions. Lastly, it is good practice to list and verify the assumptions that have been made so far. This can help you catch serious issues early on. For example, the district prices that your system out are going to be fed into a downstream machine learning system, and you assume that these prices are going to be used as such. But what if the downstream system converts the prices into categories and then uses those categories instead of the prices themselves? In this case, getting the price perfectly right is not important at all. Your system just needs to get the category right. If that's so, then the problem should have been framed as a classification task, not a regression task. You don't want to find this out after working on a regression system for months. Fortunately, after talking with the team in charge of the downstream system, you are confident that they do indeed need the actual prices, not just categories. Great. You're all set, the lights are green, you can start coding now. Get the data. It's time to get your hands dirty. Don't hesitate to pick up your laptop and walk through the code examples. As I mentioned in the preface, all the code examples in this book are open source and available online as Jupyter Notebooks, which are interactive documents containing text, images, and executable code snippets. In this book, I will assume you are running these notebooks on Google Colab, a free service that lets you run any Jupyter notebook directly online without having to install anything on your machine.
Nice.
If you want to use another online platform, or if you want to install everything locally on your own machine, please see the instructions on the book's GitHub page.
Nice.
Running the code examples using Google Colab. First, open a web browser and visit. This will lead you to Google Colab, and it will display the list of Jupyter notebooks. You will find one notebook per chapter, plus a few extra notebooks and tutorials for NumPy, Matplotlib,
So what I will do first, I will go on this website. Let me select.
First, open a web browser and visit. This will lead you...
Okay, I want to select this.
First, open a web browser and visit.
I think this is a read mode, so it is not able to. Okay, I'm understanding it. So what I can do, open this book as a PDF. Okay. You can. Okay, I will continue it, and after. Okay, let me try it together. It will be better. Okay, running the code example using Google Colab. Let me do it together. It will be better. So starting it.
You will find one notebook per chapter.
Okay, fine. Going to F11, plus F11, okay. Plus F11.
First, open a web browser and visit.
Okay, I will open the web browser and visit it. Before visiting, what I will do, I will just open once a download where I downloaded this book. This is my book. Okay, this is my book. Okay, I will open as it is, and what the page number I have to visit. Okay, fine. Page number is 74. Okay, 74. I will go there. What I can do, I think it's very difficult to. What I can do, direct touch mode, track mode is better. $74, and then press enter. Yeah. Okay, I will go on this website. It's opening now. Go column, yeah. Now what I will do, I will follow the instruction side by side. I will read the book. One side I will. Okay, fine. And side by side I will read the book and I will follow the instruction. Okay, what I can do, just close it here. Now it's good. First, let me decrease the size. What I can do, just go here, touch mode with. Okay, this is very good. Again the same issue, direct touch mode. Okay, this is good. This is really good. So first open web browser and visit. I have done this. Okay, this is your Google column. Yeah, and you will display the list of Jupyter notebooks. Yeah, displaying all the Jupyter notebooks are displaying here. Okay, you will find one notebook per chapter. Okay, I can find one notebook per chapter. First chapter was completed, the machine learning landscape. The file is there, and second chapter is also there. Okay, you will find one notebook per chapter plus few extra notebooks and tutorials for NumPy, Matplotlib. You can see at the end of the lecture. The extra Matplotlib and NumPy, pandas, every tools libraries are given. Okay, you can see extra libraries here, extra notebooks here. Okay, notebooks and tutorial for NumPy, linear algebra, differential calculus. For example, we can start it up.
This will lead you to Google Colab, and it will display the list of Jupyter notebooks for this book. You will find one notebook per chapter, plus a few extra notebooks and tutorials for NumPy, Matplotlib, pandas, linear algebra, and differential calculus. For example, if you click to end-to-end machine learning project.ipynb, the notebook from chapter 2 will open up in Google Colab.
Okay, let me do it. This is very interesting. I will just click this chapter number 2. Okay, now you can see the notebook of chapter number 2 is opening. It's taking time. Depends on your network, how fast your network. Now you can see the chapter number 2 notebook, end-to-end machine learning project. Now you can run each and every code by just Jupyter notebook. Okay, now study it.
Your notebook is composed of a list of cells. Each cell contains either executable code or text. Try double-clicking the first text cell. This will open the cell for editing. Notice Jupyter notebooks use Markdown syntax for formatting, and so on. Try modifying this text, then press Shift-Enter to see the result. Figure 2-3.
Okay, let me check it. Just click here and Shift-Enter. I think some issues there. Okay, let me enter. Let me put me here. Yeah, this is better. Okay, let me Shift-Enter. Okay, where is Shift? This is Shift, and this is Enter. Now it's running. Shift enter, run. It will run the code. For each cell you have to run separately. There is a command also, you can run all also, and by pressing that run all button. You can see here. Suppose I'm welcome to machine learning. This you can here. You can run all code also. Just press this. You can see all code are running simultaneously. Welcome to machine learning. Import sys assert sys version info. You can see here. This is also run. This also run. Download the data. This is also done. Data is downloaded. Data set is downloaded here. Take a quick look. You can see here. Every code is run together. Okay, you can see here. Nice. So definitely it's very good thing. You can try it. Okay, you can do it as much as you can. Okay, fine.
Of notebooks in Google Colab. Figure 2 in Google Colab. Next, create a new code cell by selecting Insert Code from the menu. Alternatively, you can click the plus code button bar. Hover your mouse over the bottom of a cell until you see plus code and plus text appear. Then click plus code. New code cell. Type some Python code, such as print. Then press Shift Enter to run this code.
Nice.
If you're not logged into your Google account, you'll be asked to log in now. Once you are logged in,
let me try it out. It's executing. It's executing. I think. There's a lot of code. What I can do, make a new code like plus code. Okay. Until you see plus code, then click plus code in the news. Let me do it. Okay, let me do it. I will do it here. Okay. Suppose I am doing here. I will plus code. Okay, I will press this plus code, and this will become. Now I will write it. Okay. Print hello world. Now just enter it. Okay. Now I will run it. Now executing. Okay. Yeah, or you can press this one also. It's running. It's taking time depending on the network. I think it's executing all the code. Because of that, it's taking time. Yeah, I understood. It's executing because of that. It's running all the code previously first, and then it will run my code that has print hello world. So I will wait for that time. Okay, I will run this.
You try to run the code, you'll see a security warning telling you that this notebook was not authored by Google. A malicious person could create a notebook that tries to trick you into entering your Google credentials so they can access your personal data. So before you run a notebook, always make sure you trust its author. Assuming you trust me, you can click Run Anyway.
Yeah.
Colab will then allocate a new runtime for you. This is a free virtual machine located on Google's servers that contains a bunch of tools and Python libraries, including everything you'll need for most chapters. This will take a few seconds. Next, Colab will automatically connect to this runtime and use it to execute your new. Importantly, the code runs on the runtime, not on your machine. The code's output will be displayed under the cell. Congrats, you've run some Python code on Colab.
Nice.
To insert a new code cell, you can also type Ctrl-M followed by A or B. There are many other keyboard shortcuts available. You can view and edit them by typing Ctrl-M then H. If you choose to run the notebooks on Kaggle or on your own machine using Jupyter Lab, or an IDE such as Visual Studio Code with the Jupyter extension, you will see some minor differences. Runtimes are called. The user interface and keyboard shortcuts are slightly different, etc. But switching from one to another is not too hard. Saving your code changes in your data. You can make changes to a notebook, and they will persist for as long as you keep your browser tab open. But once you close it, the changes will be lost. To avoid this, make sure you save a copy of the notebook to your Google Drive by selecting File, Copy and Drive. Alternatively, you can download the...
You can do it for saving it if you want to save it, otherwise the data may be lost. Okay, you can go File, and you can see Save a copy in Drive, and you can save one in your Google Drive. And if you haven't used the Google Drive, then you can save as a GitHub gist. You can save on that also. Okay, fine.
The notebook to your computer by selecting File, Download by PNB.
Computer also,
then you can later visit and open Notebook again. Google Colab is meant only for interactive use. You can play around in the notebooks and tweak the code as you like, but you cannot let the notebooks run unattended for a long period of time, or the runtime will be shut down, and all of its data will be lost. If the notebook generates data that you care about, make sure you download this data before the runtime shuts down. To do this, click the file's icon, find the file to download, click the vertical dots next to it, and click download. Alternatively, you can mount your Google Drive on the runtime, allowing the notebook to read and write files directly to Google Drive as if it were a local directory. For this, click the file's icon, then click the Google Drive icon and follow the on-screen instructions. Figure 2-5, downloading a file from a Google Colab runtime or mounting Google Drive. By default, your Google Drive will be mounted at content, Drive My Drive. If you want to back up a data file, simply copy it to this directory by running cp content, migrate node all content, Drive My Drive. Any command starting with a bang is treated as a shell command, not as Python code. cp is the Linux shell command to copy a file from one path to another. Note that Colab runtimes run on Linux. The power and danger of interactivity. Jupyter notebooks are interactive, and that's a great...
One second. What I can do? Now it's good. Now it's run or you can do also this. This will run. This GPU will run more faster. You seen that it was taking a lot of time through CPU, but now I'll run through GPU. It will be in few seconds. This will be done. See, it will take very less time. Okay.
Run each cell one by one. Stop at any point. Insert a cell. Play with the code. Go back and run the same cell again. I highly encourage you to do so. If you just run the cells one by one without ever playing around with them, you won't learn as fast. However, this flexibility comes at a price. It's very easy to run cells in the wrong order, or to forget to. Run a cell. If this happens, the subsequent code cells are likely to fail. For example, the very first code cell in each notebook contains setup code, so make sure you run it first, or else nothing will work.
Yeah.
If you ever run into a weird error, try restarting one time, and then run all the cells again from the beginning of the notebook.
Yeah.
This often solves the problem. If not, it's likely that one of the changes you made broke the notebook. Revert to the original notebook and try again. If it still fails, please file an issue on GitHub. Book code versus notebook code. You may sometimes notice little differences between the code in this book and the code in the notebooks. This may happen for reasons. A library may have changed slightly by the time you read these lines, or perhaps despite my best efforts I made an error in the book. Sadly, I cannot magically code a copy of this book, but I can fix the notebooks. So, if you run into an error after copying code from this book, please look for the fixed code in the notebooks. I will strive to keep them error-free and up-to-date with the latest library versions.
Nice.
The notebooks contain some extra code to beautify the figures, and to save them in high resolution for this book. You can safely ignore this extra code if you want. I optimized the code for readability and simplicity. I made it as linear and flat as possible, defining very few functions or classes. The goal is to ensure that the code you are running is generally right in front of you, and not nested within several layers of abstractions that you have to search through. This also makes it easier for you to play with the code. For simplicity, there's limited error handling, and I place some of the least common imports right where they are needed. That said, your production code will not be very different. It's a bit more modular, and with additional tests and error handling. Okay, once you're comfortable with Colab, you're ready to download the data. Download the data. In typical environments, your data would be available in a relational database or some other common data store, and spread across multiple tables, documents, files. To access it, you would first need to get your credentials and access authorizations 1, and familiarize yourself with the data schema. In this project, however, things are much simpler. You will just download a single compressed file, housing.tgz, which contains a comma-separated values file called housing.csv with all the data. Rather than manually downloading and decompressing the data, it's usually preferable to write a function that does it for you. This is useful in particular if the data changes regularly. You can write a small script that uses the function to fetch the latest data. Automating the process of fetching the data is also useful if you need to install the dataset on multiple machines. Here is the function to fetch and load the data. From pathlib import path import pandas as pd import tar file import urlib.request, def load housing data, to tarball path equal to path, if not tarball path is file, mkd equal to. erlib.quest.r retrieve with tarball.speth.
So you can see the code that is written in this book is written something similar to in here also in the notebook. See the same code you are seeing on the right side of the book. To the left side on the notebook, Google Colab notebook, you can see how to download the data. The same code is written from pathlib import path. So model pathlib import the library path, and then import pandas spd, import tar file, import urlib.request. Then a function is defined here, load housing data, while the tarball path is given the path from which we download the datasets housing dot tgz. Okay, here you can see the files. Well, let me show you the files. Yeah, the files will be shown here. I think yeah, so you see the datasets. So here the datasets you can see here the path datasets, then housing.cv is there. You can see here housing.cv. From there it will read that all data. So URL is given, http github is downloaded already. I have run that code, so because of that it downloaded that file from the github to here. The URL for this is given is just download here housing.tgz, and all other things are also being downloaded here. So when loading, now read it. Okay,
Return PD read CSV. It looks for the datasets housing.tgz.
Yeah.
If it does not find it, it creates the datasets directory. Inside the current directory, downloads the housing.
Yeah.
TGZ file from the Adron Data GitHub repository and extracts its content into the datasets directory. This creates the datasets housing directory with the housing.csv file inside it.
Yeah, you can see it.
Lastly, the function loads the CSV file into a pandas data frame object containing all the data and returns it. Take a quick look at the data structure. You start by looking at the top 5 rows of data using the data frame's head method. Figure 2-6, top 5 rows in the dataset.
So you can see this housing.head. One minute, I will show you. Yeah. Take a quick look at the dataset. Let me close it. Okay. Here, a quick look at the data structure. You can see here housing.head, the longitude, latitude. Okay. And housing median age, total rooms, total bedrooms, population, households, median income, median house value, ocean proximity. You can see everything here. Okay, so each row represent one district. Okay, one district, and there are 10 attributes. Only 4 attributes are shown because I have write housing.head. Housing.head will represent only the first 5 and that type of rows. Okay, so all 10 attributes rows are not available. They are not all shown in the screenshot. Longitude, latitude, housing, median age, total rooms, total bedrooms, population, household, median income, median house value, and ocean proximity. Okay, the info method is useful. You can see housing.info. Useful to quick description of the data, in particular the total number of rows. Okay.
Each row represents one district. There are 10 attributes: latitude, housing median age, total rooms, total bedrooms, population, households, median income, median house value, and ocean proximity. The info method is useful to get a quick description of the data, in particular the total number of rows, each attribute's type, and the number of non-null values. Memory usage.
You can see here there are 10 attributes: longitude, latitude, housing median age, total rooms, non-null. All there are non-null. The non-null data, null data is here. So there are 20,640 districts are there in the data, and each of the 10 attributes with non-null data, each has a value. The memory is 1.6 plus MB.
In this book, when a code example contains a mix of code and outputs, as is the case here, it is formatted like in the Python interpreter. For better readability, the code lines are prefixed with, and the outputs have no prefix. There are 20,640 instances in the dataset, which means that it is fairly small by machine learning standards, but it's perfect to get started. You notice that the total bedrooms attribute has only 20,433 non-null values, meaning that 200 districts are missing this feature. You will need to take care of this later. All attributes are numerical, except for ocean proximity. Its type is object, so it could hold any kind of Python object. But since you loaded this data from a CSV file, you know that it must be a text attribute.
You can see the total bedrooms are each distance on average 20,433. I have never noticed that. So you can see this. Okay. All attributes are numerical except for ocean proximity. Its type is object, so it could hold any type of Python object. But since
When you looked at the top 5 rows, you probably noticed that the values in the ocean proximity column were repetitive, which means that it is probably a categorical attribute. You can find out what categories exist and how many districts belong to each category by using the value counts method. Housing. Value counts less than 1 hour ocean. Value counts less than 136. Inland 658. The describe method shows a summary of the numerical attributes. The describe method shows are self-explanatory. Note that the null values are ignored, which measures how dispersed the values are. The 25% and 75% rows show the corresponding percentage of observations and observations fall. For example, percent of the districts have a housing median age, while 50% are lower than 18. These are often called the 25th percentile. These are often called the 25th percentile of the type of data you are dealing with. This is to plot a histogram for each numerical attribute.
so this is very good. You can see the housing was described, and it's 25% of the district have a housing median is lower than 18. You can see here housing median is 18 here for 25%. You can see here. Okay, this is 18. Okay, you can see here, and the 75% are lower 37. Okay, you can see here housing median age. So this is good, and the 75th percentile you can see third quartile. But this is really a good thing. You can use this housing.describe, and it will describe all that. Not utilizing the GPU. Fine. So you can see another quick way to get a feel of type of data you're dealing with is to plot a histogram. So you can plot histogram. Okay, so the number of okay, fine.
A histogram shows the number of instances that have a given value range. You can put this one attribute at a time, or you can call the hist method on the whole dataset, and it will plot a histogram for each numerical attribute. Import, matplotlib, pyplot, housing.hist, plt show. For each numerical attribute.
Yeah.
Looking at these histograms, you notice a few things. Median income attribute does not look like it is expressed in US dollars. After checking with the team that collected the data, you are told that the data has been scaled and capped.
Let me run this code. Let me try it out. I will what I will do. Executing what is executing. Grid search is executing. Okay. One minute. What I can do. TV4 is. Okay, randomized search and everything end to end. Okay, fine. That's cool. That's really cool. Lot of code is a lot of code. You can see the code. Okay, run it.
At 15% for higher median incomes. T-show. For each numerical attribute. At these terms, you notice a few things. First, the median income attribute does not look like it is expressed in US dollars. After checking with the team that collected the data, you are told that the data has been scaled and capped at 15% for higher median incomes, and at 0.5% for low median incomes. The numbers represent roughly tens of thousands of dollars. Working with process attributes is machine learning, and it is not necessarily a problem, but you should try to understand how the data was computed. Housing median age and the median house value are also capped. The latter may be a problem since it is your target attribute, Your machine learning algorithms may learn that prices never go beyond that limit. You need to check with your client team to see if this is a problem or not. If they tell you that they need precise predictions even beyond $500,000, then you have two options. Collect proper labels for the districts whose labels were capped. Remove those from the training set. These attributes have very different scales. We will discuss this later in this chapter, when we explore feature scaling. Finally, many histograms are skewed right. They extend much farther to the right of the median than to the left. This may make it a bit harder for some machine learning algorithms to detect patterns. Later, you'll try transforming these attributes to have more symmetrical and bell-shaped distributions. You should now have a better understanding of the kind of data you're dealing with. Wait! Before you look at the data any further, you need to create a test set, put it aside, and never look at it. Create a test set. It may seem strange to voluntarily set aside part of the data at this stage. After all, you have only taken a quick glance at the data, and surely you should learn a whole lot more about it before you decide what algorithms to use, right? This is true, but your brain is an amazing pattern detection system, which also means that it is highly prone to overfitting. If you look at the test set, you may stumble upon some seemingly interesting pattern in the test data that leads you to select a particular machine learning model. When you estimate the generalization error using that, your estimate will be too optimistic, and you will launch a system that will not perform as well as expected. This is called data snooping bias. Creating a test set is theoretically simple. Sum instances randomly, typically 20% of the data set, and set them aside. Import numpy as NP. Def shuffle and split data. Shuffled indices equal to NP random.
So
Permutation.
this code is also written here. This is the graph code. You've seen how matplotlib.py plot as PLT, and the font, axis, legend, x tick, y tick, all things are given here. And housing.histogram is given, bins 10, bins 50, fig size 12.8, and the save fig to attribute histogram plots. Okay, you can see the plots. So now create a test set. Now you can see that. 1 second, what I can do, I think this is not working. Okay, create a test set, like import numpy as NP, and the function is defined here, shuffle and split data and test ratio is taken, and okay, fine, things are done.
Test set size equal to INT test ratio. Test indices equal to shuffled indices, train indices equal to shuffled indices, return data, iloc, data. You can then train set, test set equal to the shuffle, and split data in test set. It is not perfect. If you run the program again, it will generate a different test set. Over time, you will get to see the whole data set, which is what you want to avoid. One solution is to save the test set on the first run, and then load it in subsequent runs. Another option is to set a random number generator seed, before calling end-random.permutation so that it always generates the same shuffled indices. However, both these solutions will break the next time you fetch an updated dataset. To have train test split even after updating the dataset, a common solution is to use each instance's identifier to decide whether or not it should go in the test set. For example, you could compute a hash of each instance's identifier, and put instance in the test set if the hash is lower than or equal to 2% of the maximum hash value. This ensures the test set will remain consistent across multiple runs, even if you refresh the dataset. The new test set will contain 20% of the new instances, but it will not contain any instance that was previously in the training set. Here's a possible implementation. From lib import crc. Def is ID and test. Return crc, test ratio 232. Def split dash. ID as data and test equal to ID as .apply. Return data.lcure. Unfortunately, the housing dataset does not have an identifier column. The solution is to use the row index as the ID. Housing with ID equals housing.reset index. Hashtag adds in. Call train set, test set equal to split data with ID hash. If you use the row index as a unique identifier, you need to make sure that new data gets appended to the end of the dataset and that no row ever gets deleted. If this is not possible, then you can try to use the most stable features to build a unique identifier. For example, a district's latitude and longitude are guaranteed to be stable for a few million years, so you could combine them into an ID like so. Housing with ID equal to housing 1000 plus housing train set. Test set equal to split data with ID hash. Scikit-Learn provides a few functions to split datasets into multiple subsets in various ways. The simplest function is train test split, which does pretty much the same thing as the shuffle and split data function we defined earlier, with a couple of additional features. A random state parameter that allows you to set the random generator seed. Second, You can pass it multiple datasets with an identical number of rows, and it will split them on the same entities. From Scikit-Learn.model selection. Import train test split. Train set test set equal train test split. So far we have considered purely random sampling methods. This is generally fine if your dataset is large enough, but if it is not, you run the risk of introducing a significant sampling bias. When employees at a survey company decides to call 1,000 people to ask them a few questions, they don't just pick 1,000 people randomly in a phone book. They try to ensure that these 1,000 people are representative of the whole population, with regard to the questions they want to ask. For example, the US population is 51.9% males, so a well-conducted survey in the sample, 589 males. The population is divided into homogeneous subgroups called strata, and the right number of instances are sampled from each stratum to guarantee that the test set is representative of the overall population. If the people running the survey use purely random sampling, there would be about a 10.7% chance of sampling a skewed test set with less than 48.5% female or more than 53% female. Either way, the survey results would likely be quite important attribute to predict median housing prices. You may want to ensure that the test set is representative of the various categories of incomes in the whole dataset. Since the median income is a continuous numerical attribute, you first need to create an income category attribute. Let's look at the median income histogram more closely. Most median income values are clustered around 1.5 to 6, but some median incomes go far beyond 6. It is important to have a sufficient number of instances in your dataset for each stratum, or else the estimate of a stratum's importance may be biased. This means that you should not have too many strata, and each stratum should be large enough. The following code uses the pdtut function to create an income category attribute with 5 categories. Category 1 ranges from 0 to 1.5. Category 2, housing equal to pdcut bins labels equals are represented in figure 2-9. Housing. Value counts, sort index. RPLT.
So 1 minute. You can see here the housing income cat. You can see here that code is written here. This is the extra codes up to 10.7% of getting a bad sample. You can see here. If you have a mess, roughly the same result. You can see here the income cat. np.random seed 42 samples, np.random 100 it's 100 sample size. Okay, housing income at pd dot, you can see the code pd dot cut housing median income bins 0 1.5 0.1 0.1.5 3.2 4.5 and 6 point np.info tables 1 2 3 4 5 that is represented figure 29. Housing values constants dot sort index dot bar root 0 grid true. Income category number of district variable is number of district and income category plot. So you can see the plot here. This is a plot. The same plot is will be represented here.
Bar PLT category. Scikit-Learn provides a number of splitter classes in the Scikit-Learn package that implement various strategies to split your dataset into a training set. Each splitter has a split method that returns an iterator over different training tests splitting data. Figure 2-9. Histogram of income categories. To be precise, the split method yields the training and test indices, not the data itself. Splits can be useful if you want to better estimate the performance of your model, as you will see when we discuss cross-validation later in the chapter. For example, the following code generates 10 different stratified splits of the same dataset. From Scikit-Learn.model selection. Import stratified shuffle split. Splitter equal to stratified shuffle split strat splits equal to for train index, test index and splitter split. Strat train set and housing.ilog strat test set n equal to housing.ilog. Strat test set now, you can just use the first split set equal to strat splits. Or, since stratified sampling is fairly common, there's a shorter way to get a single split using the train test split function with the stratify argument. Train set strat test set equal to train test split. Random state equal T42. Let's see if this worked as expected. You can start by looking at the income category proportions in the test set. Strat test set. Value counts. Value counts. Value counts. Value count 0.114.17. 4.1763757. 4.23 float. Compares the overall dataset and the test rated with stratified sampling using purely random sampling. As you can see, the test set stratified sampling has income category proportions almost identical to those in the full dataset, whereas the test set generated using purely random sampling is skewed. Figure 2-10. Sampling bias comparison of stratified versus purely random sampling. You won't use the income cat column again, so you might as well drop it, reverting the data back to its original state. For set-in. We spent quite a bit of time on test set generation for a good reason. This is an often neglected but critical part of a machine learning project. Moreover, many of these ideas will be useful later when we discuss cross-validation. Now it's time to move on to the next stage, exploring the data. explore and visualize the data to gain insights.
Yeah.
So far, you have only taken a quick glance at the data to get a general understanding of the kind of data you are manipulating. Now the goal is to go into a little more depth. First, make sure you have put the test set aside and you are only exploring the training set. Also, if the training set is very large, you may want to sample an exploration set to make manipulations easy and fast during the exploration phase. In this case, the training set is quite small, so you can just work directly on the full set. Since you're going to experiment with various transformations of the full training set, you should make a copy of the original so you can revert to it afterwards. Housing strat train set.copy. Visualizing geographical data. In the geographical information, it is a good idea to create a scatter plot of all the districts to visualize the data. Housing.plot.plt.show.
Nice.
Figure 2-11. A geographical scatter plot of the data. This looks like California all right, but other than that, it is hard to see any particular pattern. Setting the alpha option to 0.2 makes it much easier to visualize the places where there is a high density of data points. Housing.plot.plt. Now that's much better. You can clearly see the high density areas, namely the Bay Area and around Los Angeles and San Diego, plus a long line of fairly high density areas in the Central Valley. Our brains are very good at spotting patterns in pictures, but you may need to play around with visualization parameters to make the patterns stand out. A better visualization that highlights high density areas. Next, you look at the housing prices. The radius of each circle represents the district's population, and the color represents the price. Here you use a predefined color map called JET, which ranges from blue to red. Housing.plot, label equal to population, C equal to median house value, C equal to JET, color bar equal to true, legend equal to true, ShareX equal to false, fig size equal to PLT show. This image tells you that the housing price is very much related to the location and to the population density, as you probably knew already. A clustering algorithm should be useful for detecting the main cluster and for adding new features that measure the proximity to the cluster centers. The ocean proximity attribute may be useful as well, although in Northern California, prices in coastal districts are not too high, so it is not a simple rule.
Nice.
Figure 2-13. California housing prices, red is expensive. Blue is cheap. Larger circles indicate areas with a larger population. Look for correlations. Since the dataset is not too large, you can easily compute the standard correlation coefficient between every pair of attributes using the core method. Now you can look at how much each attribute correlates with the median house value. The correlation coefficient ranges from -1 to 1. When it is close to 1, it means that there is a strong positive correlation. For example, the median house value tends to go up and the median income goes up. When the coefficient is close to -1, it means that there is a strong negative correlation. You can see a small negative correlation between the latitude and the median house value. Finally, coefficients close to 0 mean that there is no linear correlation. Another way to check for correlation between attributes is to use the pandas scatter matrix function, which plots every numerical attribute against every other numerical attribute. Since there are now 11 numerical attributes, you would get 11 to the power of 2 equal to 121 plots, which would not fit on a page. So you decide to focus on a few promising attributes that seem most correlated with the median housing value. From pandas. Plotting import scatter matrix. Scatter matrix, fig size equal to figure 2-14. This scatter attribute against every other numerical attribute, plus a histogram of each numerical attribute's values on the main diagonal. The main diagonal would be full of straight lines if pandas plotted each variable against itself, which would not be very useful. So instead the pandas displays a histogram of each attribute. Looking at the correlation scatter plots, it seems like the most promising attribute to predict the median house value is the median income. So you zoom in on their scatter plot. Housing.plot.plto show. Figure 2-15. Median income versus median house value.
Nice.
This plot reveals a few things. First, the correlation is indeed quite strong. You can clearly see the upward trend, and the points are not too dispersed. Second, the price cap you noticed earlier is clearly visible as a horizontal line at $500,000. But the plot also reveals other less obvious straight lines. A horizontal line around $450,000. Another around $350,000. You may want to try removing the corresponding districts to prevent your algorithms from learning to reproduce these data. It may completely miss out on nonlinear relationships. Figure 2-16 shows a variety of datasets along with their correlation coefficient. Note how all the plots of the bottom row have a correlation coefficient equal to 0. Despite the fact that their axes are clearly not independent, these are examples of nonlinear relationships. Also, the second row shows examples where the correlation coefficient is equal to 1 or -1. Notice that this has nothing to do with the slope. For example, your height in inches has a correlation coefficient of 1 with your height in feet or in nanometers. Figure 2-16. Standard correlation coefficient of various datasets. Experiment attribute combinations. Hopefully the previous sections gave you an idea of a few ways you can explore the data and gain insights. You identified a few data correlations you want to clean up before feeding the data to a machine learning algorithm, and you found interesting correlations between attributes, in particular with the target attribute. You also noticed that some attributes have a skewed right distribution, so you may want to transform them. Of course, Your mileage will vary considerably with each project, but the general ideas are similar. One last thing you may want to do before preparing the data for machine learning algorithms is to try out various attribute combinations. For example, the total number of rooms in a district is not very useful if you don't know how many households there are. What you really want is the number of rooms per household. Similarly, the total number of bedrooms by itself is not very useful. You probably want to compare it to the number of rooms. And the population per household also is an interesting attribute combination to look at. You create these new attributes as follows. Housing equal to housing, 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 equal to housing, and housing, housing, and equal to housing, housing. And then you look at the correlation matrix again. Hey, not bad. The new bedrooms ratio attribute is much more correlated with the median.
Nice. You can see here housing, the same code that was written here. Total bedrooms, prepare data for machine learning. Total bedrooms, rooms. This is okay. Option 3. Total bedrooms. Longitude array A is given. Fine. Okay, rooms per house, housing total rooms divided by housing households and housing bedrooms ratio, housing total bedrooms divided by housing total rooms bedroom ratio, and people per house, housing population divided by housing households. Okay, then you look at the correlation matrix again. This you can see the matrix here. Median house values, median income, rooms per house, median house values, sort values, ascending false. Okay. Okay, fine. Nice.
House value than the number of rooms or bedrooms. Apparently, houses with a lower bedroom-room ratio tend to be more expensive. The number of rooms per house is also more informative than the total number of rooms in a district. Obviously, the larger the houses, the more expensive they are. This round of exploration does not have to be absolutely thorough. The point is to start off on the right foot and quickly gain insights that will help you get a first reasonably good prototype. But this is an iterative process. Once you get a prototype up and running, you can analyze its output to gain more insights and come back to this exploration step. Prepare the data for machine learning algorithms. It's time to prepare the data for your machine learning algorithms. Instead of doing this manually, you should write functions for this purpose, for several good reasons. This will allow you to reproduce these transformations easily on any dataset. You will gradually build a library of transformation functions that you can reuse in future projects. You can use these functions in the system to transform the new data before feeding it to your algorithms. This will make it possible for you to easily try various transformations and see which combination of transformations works best. But first, revert to a clean training set. You should also separate the predictors and the labels, since you don't necessarily want to apply the same transformations to the predictors, and the target values creates a copy of the data and does not affect strat train set. Strat train set drop. Housing labels strat train set. Copy. Clean the data. Most machine learning algorithms cannot work with missing features, so you'll need to take care of these. For example, you noticed earlier that the total bedrooms attribute has some missing values. You have 3 options to fix this. 1. Get rid of the corresponding districts. 2. Get rid of the whole attribute. Set the missing values to some value. This is called imputation. You can accomplish this easily using the pandas data frames dropna, drop, and fillna methods. Housing dropna. In place equal to true, hashtag option 1. Housing drop hashtag option 2, median housing. Median hashtag option 3, housing. Fillna. You decide to go for option 3 since it is the least destructive. But instead of the preceding code, you will use a handy Scikit-Learn class, simple imputer, that it will store the median value of each feature. This will make it possible to impute missing values not only on the training set, but also on the validation set, the test set, and any new data fed to the model. To use it, first you need to create a simple imputer instance. specifying that you want to replace each attribute's missing values with the median of that attribute. From Scikit-Learn.impute import simple-imputer. Imputer equal to simple-imputer. Since the median can only be computed on numerical attributes, you then need to create a copy of the data with only the numerical attributes. Housing num equal to housing.select types. Now you can fit the imputer instance to the training data using the fit method, imputer.fit. The imputer has simply computed the median of each attribute and stored the result in its statistics instance variable. Only the total bedrooms attribute had missing values, but you cannot be sure that there won't be any missing values in new data after the system goes live, so it is safer to apply the imputer to all the numerical attributes. Imputer.statistics. Array. W-array. Now you can use this trained imputer to transform the training set by replacing missing values with the learned medians. Imputer.transform. Missing values can also be replaced with the mean value, or with the most frequent value, or with a constant value. The last two strategies support non-numerical data. There are also more powerful imputers available in the Scikit-Learn.impute package. KNN imputer replaces each missing value with the mean of the k nearest neighbor's values for that feature. The distance is based on all the available features. Iterative imputer trains a regression model per feature to predict the missing values based on all the other available features. It then trains the model again on the updated data, and repeats the process several times, improving the models and the replacement values at each iteration. Scikit-Learn design. Scikit-Learn's API is remarkably well designed. These are design principles. Consistency. All objects share a consistent and simple interface. Estimators. Any object that can estimate some parameters based on a dataset is called an estimator. The estimation itself is performed by the fit method, and it takes a dataset as a parameter, or two for supervised learning algorithms. The second dataset contains the labels. Any other parameter needed to guide the estimation process is considered a hyperparameter, and it must be set as an instance variable. Transformers. Some estimators can also transform a dataset. These are called transformers. Once again, the API is simple. The transformation is performed by the transform method with the dataset to transform as a parameter. It returns the transformed dataset. This transformation generally relies on the learned parameters, as is the case for a simple imputer. All transformers also have a convenience method called fit transform, which is equivalent to calling fit, and then transform is optimized and runs much faster. Predictors. Finally, some estimators, given a dataset, are making predictions. They are called predictors. For example, the linear regression model in the previous chapter was a predictor. Given a country's GDP per capita, it predicted life satisfaction. A predictor has a predict method that takes a dataset of new instances and returns a dataset of corresponding predictions. It also has a score method that measures the quality of the predictions, given a test set. Inspection. All the estimator's hyperparameters are accessible directly via public instance variables, and all the estimator's learned parameters are accessible via public instance variables with an underscore suffix. Non-proliferation of classes datasets are represented as numpy arrays or scipy sparse matrices instead of homemade classes. Hyperparameters are just regular Python strings or numbers. Composition existing in building blocks are reused as much as possible. For example, it is easy to create a pipeline estimator from an arbitrary sequence of transformers, followed by a final estimator, as you will see. Sensible default Scikit-Learn provides reasonable default values for most parameters, making it easy to quickly create a baseline working system. Scikit-Learn transformers output numpy arrays, even when they are fed pandas data frames as input. So, the output of imputer.transform is a numpy array. X has neither column names nor index. Luckily, it's not too hard to wrap X in a data frame and recover the column names and index from housing them. Housing tr equal to pd data frame. Handling text and categorical attributes. So far, we have only dealt with numerical attributes, but your data may also contain text attributes.
Okay, fine. So today is enough. I am on the page number 71. That's so good. So I will continue from here. Handling text and categorical attributes. Okay, I think in the notebook it is here. Housing catno. Yeah. Housing ocean proximity. I don't know where the code is written. They say really. Housing drop now. Okay, this is option. Okay, fine. It's very difficult to read from this. It's really, because the thing is that I'm using my tab and using the casting feature, because of that it's lagging. That's cool. Imputer is given. Yeah. Housing is selected types. Status 6 given. median value is given, transform is given, imputed to transform. You can see how is transform. TR, yeah, housing TR. This is the imputed strategy. TR not shown in the book. Housing cat, housing ocean proximity, housing cat dot head. You can see this is the code of this. So I will start from here, 63, line number 63. Okay, so it's enough for today, but I will do continuous the study after some break. Okay, so starting it. Okay, from handling text.
Handling text and categorical attributes. So far, we have only dealt with numerical attributes, but your data may also contain text attributes. In this dataset, there is just one, the ocean proximity attribute.
Yeah.
Let's look at its value for the first few instances. Housing cat equal to housing cat head. Ocean proximity, 13,096, near bay 14,973, less than 1 hour ocean. 1,785, inland, 14,589, inland 20,507, and to our limited number of possible values, each of which represents a category. So this attribute is a categorical attribute.
Yeah.
Most machine learning algorithms prefer to work with numbers, so let's convert these categories from text to numbers. For this, we can use Scikit-Learn's ordinal encoder class.
Nice.
From Scikit-Learn preprocessing import ordinal encoder. Ordinal encoder equal to ordinal encoder housing cat.
Whatever is written in the book is same code is executed. You can one second. Let me put here. You can see here like this code is written here from Scikit-Learn preprocessing import ordinal encoder. Ordinal encoder is equal to ordinal encoder and housing cat encoder. You can see here the same code here written here and is also run. You can see the output here. One second. Okay, fine. Nice.
Equal to ordinal encoder.fit transform. Here's what the first few encoded values in housing cat encoded look like.
This one.
Housing cat encoded array. You can get the list of categories using the categories instance variable. It is a list containing a 1D array of categories for each categorical attribute.
Nice.
Ordinal encoder.categories. One issue with this representation is that ML algorithms will assume that two nearby values are more similar than two distant values. This may be fine in some cases, but it is obviously not the case for the ocean proximity column. To fix this issue, a common solution is to create one binary attribute per category, one attribute equal to 1 when the category is less than 1 hour ocean, another attribute equal to 1 when the category is inland, and so on. This is called one-hot encoding, because only one attribute will be equal to 1, while the others will be 0.
Yeah.
The new attributes are sometimes called demi-attributes. Scikit-Learn provides a one-hot encoder class to convert categorical values into one-hot vectors. From Scikit-Learn preprocessing import one-hot encoder. Cat encoder equal to one-hot encoder housing ketone hot equal to cat encoder.fit transform. By default, the output of a one-hot encoder is a SciPy sparse matrix, instead of a NumPy array, housing ketone hot less than 16,512 times sparse matrix of type class. NumPy.matrix of type class, NumPy 12 times sparse row format. A sparse matrix is a very efficient representation for matrices that contain mostly zeros. Indeed, internally it only stores the non-zero values and their positions. When a categorical attribute has hundreds or thousands of categories, one-hot encoding it results in a very large matrix full of OS, except for a single one per row. In this case, a sparse matrix is exactly what you need. It will save plenty of memory and speed up computations. You can use a sparse matrix mostly like a normal 2D array, but if you want to convert it to a NumPy array, just call the TOR method, housing ketone hot TOR array. Alternatively, you can set...
for if you want to convert the dense NumPy array to dense, you can use this two array method. Like in the given code, you can see here housing cat one hot two array, then it will be converted into that NumPy array, the dense NumPy array. You can see here. Alternative, you can set sparse false, sparse output false. When creating one hot encoder, the sparse hyperparameter was renamed to sparse output. Fine.
Sparse equal to false when creating the one-hot encoder, in which case the transform method will return a regular NumPy array directly. As with the ordinal encoder, you can get the list of categories using the encoder's categories instance variable. Cat encoder.categories. Array. Type equal to object. Pandas has a function called getDummies, which also converts each categorical feature into a one-hot representation, with one binary feature per category. dftest equal to pd dataframe.pd getDummies. 0, 1. Ocean proximity inland, ocean proximity near bay. 10, 0, 1. It looks nice and simple. So why?
So here you can see the table. The open proximity in length, for 0 it is true. Okay, then open proximity nearby is false, and for same for 1 it is false for inland, and for nearby is true. It's just opposite of that. So it looks like nice and simple.
Not use it instead of one-hot encoder?
Yeah.
Well, advantage of one-hot encoder is that it remembers which categories it was trained on. This is very important because once your model is in production, it should be fed exactly the same features as during training, no more, no less. Look what our trained cat encoder outputs when we make it transform the same DF test, not fit transform, cat encoder.transform. Array, see the difference? Yet dummy saw only 2 categories, so it output 2 columns, whereas one hot encoder output 1 column per learned category, in the right order. Moreover, if you feed get dummies a data frame containing an unknown category, it will happily generate a column for it. DF test unknown equal to PD. Data frame pd.get. Dummy 01 ocean proximity less than 2 hours, ocean proximity island, 1001. But one hot encoder is smarter. It will detect the unknown category and raise an exception. If you prefer, you can set the handle unknown hyperparameter to ignore, in which case it will just represent the unknown category with zeros. Cat encoder.handle unknown equal to ignore cat encoder.transform array. If a categorical attribute has a large number of possible categories, then one hot encoding will result in a large number of input features. This may slow down training and degrade performance. If this happens, you may want to replace the categorical input with useful numerical features related to the categories. For example, you could replace the ocean proximity feature with the distance to the ocean. Alternatively, you can use one of the encoders provided by the category encoders package on GitHub.
Yeah.
Or, when dealing with neural networks, you can replace each category with a learnable low-dimensional vector called an embedding. This is an example of representation learning. When you fit any Scikit-Learn estimator using a data frame, the estimator stores the column names and the feature names in attribute. Scikit-Learn then ensures that any data frame fed to this estimator after that, or predict, has the same column names. Transformers also provide a getFeatureNamesOut method that you can use to build a data frame around the transformer's output. Cat encoder.featureName is in array type equal to object cat encoder.getFeatureNamesOut. Array type equal to object df output equal to PD data frame.
Nice.
Columns equal to cat
Here
encoder.get.
you can see the array. Each category is here. Ocean proximity less than 1 ocean. Ocean proximity in lane. Ocean proximity island. Ocean proximity near bay, and ocean proximity on your ocean. The D type object. And the df output, you can see the pd dot data frame, and the same code is written here. You can see the same code here, how it's executed. You can see here. See, nice, and the output is also there. The df output pd dot data frame cat encoder dot transform df test unknown, that is defined already there above. Okay, and columns cat encoder dot get feature names output index df test unknown dot index. The df output you can see here. Okay,
Feature names out. Index equal to df test unknown dot index. Feature scaling and transformation. One of the most important transformations you need to apply to your data is feature scaling. With few exceptions, machine learning algorithms don't perform well when the input numerical attributes have very different scales. This is the case for the housing data. The total number of rooms ranges from about 6 to 39,320,
nice.
while the median incomes only range from 0 to 15. Without any scaling, most models will be biased toward ignoring the median income and focusing more on the number of rooms. There are 2 common ways to get all attributes to have the same scale: min-max scaling and standardization. As with all estimators, it is important to fit the scalars to the training data only. Never use fit or fit transform for anything else than the training set.
Nice.
Once you have a trained scalar, you can then use it to transform any other set, including the validation set, the test set, and new data. Note that while the training set values will always be scaled to the specified range, if new data contains outliers, these may end up scaled outside the range. If you want to avoid this, just set the clip hyperparameter to true.
Nice.
Min-max scaling is the simplest. For each attribute, the values are shifted and rescaled so that they end up ranging from 0 to 1. This is performed by subtracting the min value and dividing by the difference between the min and the max. Scikit-Learn provides a transformer called min-max scalar for this. It has a feature range hyperparameter that lets you change the range if for some reason you don't want 0 to 1. It's quite easy to use. From Scikit-Learn.preprocessing import min-max scalar. Min-max scalar equal to min-max scalar. Housing num min-max scaled equal to min-max scalar.fit transform. Standardization is different. First it subtracts the mean value, then it divides the result by the standard deviation. Unlike min-max scaling, standardization does not restrict values to a specific range. However, standardization is much less affected by outliers. For example, suppose a district has a median income equal to 100 instead of the usual 0 to 15. Min-max, scaling to the 0 to 1 range, would map this outlier down to 1, and it would crush all the other values down to 0 to 0.1%, whereas standardization would not be much affected. Scikit-Learn provides a transformer called standard scaler for standardization. From Scikit-Learn.preprocessing, import standard scaler. std scaler equal to standard scaler housing num std.
Same code you can see here. std scaler, you can see here. The same code is written here. From Scikit-Learn.preprocessing, import standard scaler and std scaler, standard scaler, and the method is called here. It is stored in the variable standard std underscore scaler. Housing number standard scaled is equal to std scaler dot fit transform housing number. So it's fitted. Now you can see the graph now next in this code.
Scaled equal to std scaler dot fit transform. If you want to scale a sparse matrix without converting it to dense matrix first, you can use a standard scaler with its with mean hyperparameter set to false. It will only divide the data by the standard deviation, without subtracting the mean. The distribution has a heavy tail. Both min-max scaling and standardization will squash most values into a small range. Machine learning models generally don't like this at all, as you will see in Chapter 4. So before you scale the feature, you should first transform it to shrink the heavy tail, and if possible to make the distribution roughly symmetrical.
Nice.
For example, a common way to do this for positive features with a heavy tail to the right is to replace the feature with its square root. If the feature has a really long and heavy tail, such as a power law distribution, then replacing the feature with its logarithm may help. For example, the population feature roughly follows a power law. Districts with 10,000 inhabitants are only 10 times less frequent than districts with 1,000 inhabitants, not exponentially less frequent. Figure 2-17 shows how much better this feature looks when you compute its log. It's very close to a Gaussian distribution.
That is basic.
Figure 2-17. Transforming a feature to make it closer to a Gaussian distribution.
Basic.
Another approach to handle heavy-tailed features consists in bucketizing the feature. This means chopping its distribution into roughly equal-sized buckets, and replacing each feature value with the index of the bucket it belongs to, much like we did to create the InConeCat feature. For example, you could replace each value with its percentile. Bucketizing with equal-sized buckets results in a feature with an almost uniform distribution, so there's no need for further scaling. Or you can just divide by the number of buckets to force the values to the 0 to 1 range. When a feature has a multimodal distribution, such as the housing median age feature, it can also be helpful to bucketize it, but this time treating the bucket IDs as categories, rather than as numerical values. This means that the bucket indices must be encoded, for example using a one-hot encoder. This approach will allow the regression model to more easily learn different rules for different ranges of this feature value. For example, perhaps houses built around 35 years ago have a peculiar style that fell out of fashion, and therefore they're cheaper than their age alone would suggest. Another approach to transforming multimodal distributions is to add a feature for each of the modes, representing the similarity between the housing median age and that particular mode. The similarity measure is typically computed using a radial basis function, any function that depends only on the distance between the input value and a fixed point. The most commonly used RBF is the Gaussian RBF, whose output value decays exponentially as the input value moves away from the fixed point. For example, the Gaussian RBF similarity between the housing age x and 35 is given by the equation xp. The hyperparameter y determines how quickly the similarity measure decays as x moves away from 35.
Nice.
Using Scikit-Learn's RBF kernel function, you can create a new Gaussian RBF feature measuring the similarity between the housing median age and 35.
35, yeah.
From Scikit-Learn.metrics. Pairwise import RBF kernel. Age simul 35 equal to RBF kernel, gamma equal to 0, 1. Figure 2-18 shows this new feature as a function of the housing median age. It also shows what the feature would look like if you used a smaller gamma value. As the chart shows, the new age similarity feature peaks at 35, right around the spike in the housing median age distribution. If this particular age group is well correlated with lower prices, there's a good chance that this new feature will help.
Nice.
Figure 2-18. Gaussian RBF feature measuring the similarity between the housing median age and 35. So far we've only looked at the input features, but the target values may also need to be transformed. For example, if the target distribution has a heavy tail, you may choose to replace the target with its logarithm. But if you do, the regression model will now predict the log of the median house value, not the median house value itself. You will need to compute the exponential of the model's prediction if you want the predicted median house value. Luckily, most of Scikit-Learn's transformers have an inverse transform method, making it easy to compute the inverse of their transformations. For example, the following code example shows how to scale the labels using a standard scaler, then train a simple linear regression model on the resulting scaled labels, and use it to make predictions on some new data, which we transform back to the original scale using the trained scaler's inverse transform method.
Nice.
Note that we convert the labels from a pandas series to a data frame. Standard scaler expects 2D inputs. Also, in this example, we just trained the model on a single raw input feature, for simplicity, from Scikit-Learn.linear model. Import linear regression. Target scalar equal to standard scalar scaled labels equal to target scalar.fit transform. Model linear regression model.fit scaled labels some new data equal to housing. ILO hashtag pretend this is new data. Scaled predictions equal to model.predict predictions equal to target scalar.inverse transform. This works fine, but a simpler option is to use a transform target regressor. We just need to construct it, giving it the regression model and the label transformer, then fit it on the training set, using the original unscaled labels. It will automatically use the transformer to scale the labels and train the regression model on the resulting scaled labels, just like we did previously.
Nice.
Then, when we want to make a prediction, it will call the regression model's predict method, and use the scalar's inverse transform method to produce the prediction.
Nice.
From Scikit-Learn.compose import transformed target regressor.
Same code is here.
Model equal to transform target regressor, transformer standard scalar, model.fit, housing labels, predictions equal to model.predict. Custom transformers. Although Scikit-Learn provides many useful transformers, you will need to write your own for tasks such as custom transformations, cleanup operations, or combining specific attributes. For transformations that don't require any training, you can just write a function that takes a NumPy array as its input and outputs the transformed array. For example, as discussed in the previous section, it's often a good idea to transform features with heavy-tailed distributions by replacing them with their logarithm. Let's create a log transformer and apply it to the population feature. From Scikit-Learn.preprocessing, import function transformer. Log transformer equal to function transformer log pop equal to log transformer.transform. The inverse func argument is optional. It lets you specify an inverse transform function, for example, if you plan to use your transformer in a transform target regressor. Your transformation function can take hyperparameters as additional arguments. For example, here's how to create a transformer that computes the same Gaussian RBF similarity measure as earlier. RBF transformer equal to function transformer, gamma equal to 0.1, age simil 35 equal to RBF transformer.transform. Note that there's no inverse function for the RBF kernel, since there are always two values at a given distance from a fixed point. Also note that RBF kernel does not treat the features separately. If you pass it an array with two features, it will measure the 2D distance to measure similarity. For example, here's how to add a feature that will measure the geographic similarity between each district and San Francisco. SF chords equal to 37.7749 minus 102.41 SF transformer equal to function transformer equal to SF transform. Custom transformers are also useful to combine features. For example, here's a function transformer that computes the ratio between the input features 0 and 1. Ratio transformer equal to function transformer. X ratio transformer.transform. Array. Function transformer is very handy. But what if you would like your transformer to be trainable, learning some parameters in the fit method and using them later in the transform method? For this, you need to write a custom class. Scikit-Learn relies on duck typing, so this class does not have to inherit from any particular base class. All it needs is three methods, fit transform and fit transform. You can get fit transform for free by simply adding transformer mixin as a base class. The default implementation will just call fit and then transform. If you add base estimator as a base class, you will also get two extra methods, get params and set params. These will be useful for automatic hyperparameter tuning. For example, here's a custom transformer that acts much like the standard scalar. From Scikit-Learn.base import base estimator, transformer mixin from Scikit-Learn.utils.validation import check array. Check is fitted class standard scalar clone. Definite, hashtag no args or quarks. Self with mean equal to with mean def fit. Even though we don't use it, x equal to check array, hashtags that x is an array with finite float values self.mean, equal to 10th mean self.scale, equal to 10th mean self, equal to 10th shape hashtag every estimator stores this in fit return self. Always return self. Def transform, check is fitted, hashtag looks for learned attributes x equal to check array assert self.features in. If self with mean, x equal to x self.mean,
Nice.
return x self.scale, 10th shape. Here are a few things to note. The Scikit-Learn.utils.validation package contains several functions we can use to validate the inputs. For simplicity, we will skip such tests in the rest of this book, but production code should have them. Scikit-Learn pipelines require the fit method to have two arguments x and y, which is why we need the y equal to none argument, even though we don't use y. All Scikit-Learn estimators set in features in the fit method, and they ensure that the data passed to transform or predict has this number of features. The fit method must return self. This implementation is not 100% complete. All estimators should set feature name as in the fit method when they are passed a data frame. Moreover, all transformers should provide a get feature names out method, as well as an inverse transform method when their transformation can be reversed. See the last exercise at the end of this chapter for more details.
Nice.
A custom transformer can use other estimators in its implementation. For example, the following code demonstrates custom transformer that uses a key-means clusterer in the fit method to identify the main clusters in the training data, and then uses RBF kernel in the transform method to measure how similar each sample is to each cluster center. From Scikit-Learn.cluster import kmeans. Class cluster similarity. Definite. Self.n clusters. Equal to n cluster self.gamma self random state. Equal to random state def fit. Self to k-means equal to key-means self. TAC means return self, hashtag always return self, def transform, return RBF kernel def get feature names out. Return you can check whether your custom estimator respects Scikit-Learn's API by passing an instance to check estimator from the Scikit-Learn.utils estimator checks. Package. For the full API, check out. As you will see in Chapter 9, K-means is a clustering algorithm that locates clusters in the data. How many it searches for is controlled by the n-clusters hyperparameter. After training, the cluster centers are available via the cluster centers attribute. The fit method of K-means supports an optional argument sample weight, which lets the user specify the relative weights of the samples. K-means is a stochastic algorithm, meaning that it relies on randomness to locate the clusters, so if you want reproducible results, you must set the random state parameter. As you can see, despite the complexity of the task, the code is fairly straightforward. Now let's use this custom transformer, cluster simil equal to cluster similarities equal to cluster simil, fit transform, sample weight equal to housing labels. This code creates a cluster similarity transformer, setting the number of clusters to 10. Then it calls fit transform with the latitude and longitude of every district in the training set, weighting each district by its median house value. The transformer uses k-means to locate the clusters, then measures the Gaussian RBF similarity between each district and all 10 cluster centers. The result is a matrix with 1 row per district and 1 column per cluster. Let's look at the first 3 rows. Rounding to 2 decimal places. Similarities round array, 0.14 mon, 0.11111, shows the 10 cluster centers found by k-means. The district similarity to their closest cluster center. As you can see, most clusters are located in highly populated and expensive areas. Figure 2-19. Gaussian RBF similarity to the nearest cluster center. Transformation pipelines. As you can see, there are many data transformation steps that need to be executed in the right order. Fortunately, Scikit-Learn provides the pipeline class to help with such sequences of transformations. Here is a small pipeline for numerical attributes, which will first impute then scale the input features. From Scikit-Learn pipeline import pipeline. Num pipeline equal to pipeline. The pipeline constructor...
Okay. I will continue this transformation pipeline in the next session. So it's time to just tell which page I have completed. This is time to practice some question and make a podcast of the whatever I learn. Okay. So I think so. That's page number 83. Okay. And okay, fine. I will go back, and then reopen it. Not this. Reopen the page. Yeah. Make it big. Okay. All things will become. Okay. 112. Page number 112. I have completed till here. No, 111. Okay. So I'm going to summarize the whatever I learned today. Okay. In this chapter number 2. Okay. So going to summarize it, deep dive, bullet points, and select pages. Not pages, chapters will be okay, because we will select chapters. Now chapter number 2, I will select only those till where I completed. Okay, in the data transformation timeline. Okay, I will remove this. Fine tutorial model, launch, fire it out, and okay, let me complete this also, then it will be completed whole. Okay, till transformation pipeline I will do it. Okay, it will be better. Okay, I will summarize till chapter number 2, transformation pipeline, and from tomorrow I will continue this select and train a model till the end of the lecture. Half of the chapter 2 is completed, and half of the chapter I will continue tomorrow. Okay, fine. Now going to create summary. Before we create it, what I can do, I will just fine. Okay, continue it. Let it summarize. Okay, continue it from transformation pipeline.
Transformation pipelines. As you can see, there are many data transformation steps that need to be executed in the right order. Fortunately, Scikit-Learn provides the pipeline class to help with such sequences of transformations. Here is a small pipeline for numerical attributes, which will first impute then scale the input features from Scikit-Learn.pipeline import pipeline.
Yeah.
Num pipeline equal to pipeline. The pipeline constructor takes a list of name estimator pairs.
Here you can see the code. Impute, simple imputer is used. Okay, strategy is median, and standardize standard scale. Okay, these things are used here. That's cool. Okay, now the pipeline constructor.
The pipeline constructor takes a list of name estimator pairs defining a sequence of steps. The names can be anything you like, as long as they are unique and don't contain double underscores. They will be useful later when we discuss hyperparameter tuning. The estimators must all be transformers method, except for the last one, which can be anything, a transformer, a predictor, or any other type of estimator. In a Jupyter notebook, if you import Scikit-Learn and run Scikit-Learn, set config all Scikit-Learn estimators will be rendered as interactive diagrams. This is particularly useful for visualizing pipelines. To visualize num pipeline, run a cell with num pipeline as the last line. Clicking an estimator will show more details. If you don't want to name the transformers, you can use the make pipeline function instead. It takes transformers as positional arguments and creates a pipeline using the names of the transformers classes in lowercase and without underscores. From Scikit-Learn top pipeline, import make pipeline. Num pipeline equal to make pipeline. Standard scalar. If multiple transformers have the same name, an index is appended to their names. When you call the pipeline's fit method, it calls fit transform sequentially on all the transformers, passing the output of each call as the parameter to the next call until it reaches the final estimator, for which it just calls the fit method. The pipeline exposes the same methods as the final estimator. In this example, the last estimator is a standard scalar, which is a transformer, so the pipeline also acts like a transformer. If you call the pipeline's transform method, it will sequentially apply all the transformations to the data. If the last estimator were a predictor instead of a transformer, then the pipeline would have a predict method rather than a transform method. Calling it would sequentially apply all the transformations to the data and pass the result to the predictor's predict method. Let's call the pipeline's fit transform method and look at the output's first two rows, rounded to 2 decimal places. As you saw earlier, if you want to recover a nice data frame, you can use the pipeline's get feature names out method. df housing num prepared equal to pd data frame, housing num prepared, index housing num dot index. Pipeline support indexing, for example. Pipeline returns the second estimator in the pipeline, and pipeline returns a pipeline object containing all but the last estimator. You can also access the estimators via the steps attribute, which is a list of name estimator pairs, or via the named steps dictionary attribute, which maps the named estimators. For example, num pipeline returns the estimator named simplimputer. So far, we have handled the categorical columns and the numerical columns separately. It would be more convenient to have a single transformer capable of handling all columns, applying the appropriate transformations to each column. For this, you can use a column transformer. For example, the following column transformer will apply num pipeline numerical attributes and cat pipeline to the categorical attribute. From scikit-learn.compose import column transformer. Numattribs equal to catattribs equal to cat pipeline equal to make pipeline. One hot encoder. Preprocessing equal to column transformer. First, we import the column transformer class. Then we define the list of numerical and categorical column names and construct a simple pipeline for categorical attributes. Lastly, we construct a column transformer. Its constructor requires a list of triplets, each containing a name, a transformer, and a list of names of columns that the transformer should be applied to. Instead of using a transformer, you can specify string drop if you want the columns to be dropped, or you can specify a path-through if you want the columns to be left untouched. By default, the remaining columns will be dropped, but you can set the remainder hyperparameter to any transformer if you want these columns to be handled differently. Since listing all the column names is not very convenient, Scikit-Learn provides a make column selector function that returns a selector function you can use to automatically select all the features of a given type, such as numerical or categorical. You can pass this selector function to the column transformer instead of column names or indices. Moreover, if you don't care about naming the transformers, you can use make column transformer, which chooses the names for you, just like make pipeline does. For example, the following code creates the same column transformer as earlier, except the transformers are automatically named pipeline 1 and pipeline -2 instead of num and cat. From scikit-learn.compose import make column selector, make column transformer. Preprocessing equal to make column transformer. Now we're ready to apply this column transformer to the housing data. Housing prepared equal to preprocessing fit transform. Great. We have a preprocessing pipeline that takes the entire training dataset and applies each transformer to the appropriate columns, then concatenates the transformed columns horizontally. Once again, this returns a numpy array, but you can get the column names using preprocessing get feature names out, and wrap the data in a nice data frame as we did before. The one hot encoder returns a sparse matrix and the num pipeline returns a dense matrix. When there is such a mix of sparse and dense matrices, the column transformer estimates the density of the final matrix, and it returns a sparse matrix if the density is lower than a given threshold. In this example, it returns a dense matrix.
Nice.
Your project is going really well and you're almost ready to train some models. You now want to create a single pipeline that will perform all the transformations you've experimented with up to now. Let's recap what the pipeline will do and why.
Nice.
Missing values in numerical features will be imputed by replacing them with Boolean, as most ML algorithms don't expect missing values. In categorical features, missing values will be replaced by the most frequent category. The categorical feature will be one hot encoded, as most ML algorithms only accept numerical inputs. A few ratio features will be computed and added: bedrooms ratio, rooms per house, and people per house. Hopefully these will better correlate the median house value, and thereby help the ML models. A few cluster similarity features will also be added. These will likely be more useful to the model than latitude and longitude. Features with a long tail will be replaced by their logarithm, as most models prefer features with roughly uniform or Gaussian distributions. All numerical features will be standardized, as most ML algorithms prefer when all features have roughly the same scale. The code that builds the pipeline to do all of this should look familiar to you by now. Def column ratio. Return x, def ratio name. Return hashtag feature names out def ratio pipeline. Return make pipeline. Function transformer. Standard scalar. Log pipeline. Equal to make pipeline, function transformer, standard scalar. Cluster simil equal to cluster similarity default num pipeline. Equal to make pipeline. Preprocessing column transformer, standard scalar. Remainder equal to default num pipeline. Hashtag 1 column remaining. Housing median age. If you run this column transformer, it performs all the transformations and outputs a numpy array with 24 features. Housing prepared equal to preprocessing.fit. Transform housing prepared. Shape preprocessing. Cartesian cluster 9 similarity. Cartesian proximity less than 1 hour ocean. Cartesian proximity land. Cartesian proximity island. Cartesian proximity or bay. Cartesian proximity or ocean. Remainder housing median age. Type equal to object. Select and train a model.
Okay. Till here I completed. Now from tomorrow I will go for ahead of it, select and train a model and follow topics of this chapter number 2. Okay. Now it's time to see see the summary of the chapter. Okay. Summary now, and you can zoom in.
Select and
Okay, fine. 9th of June. Okay, I'm going to read the summary. Okay, fine.
1. Foundations of a machine learning project. Project overview. To illustrate end-to-end workflows, the project simulates a data scientist at a housing company tasked with predicting median housing prices based on 1990 California census data. Project lifecycle. The methodology follows 8 distinct phases: defining the big picture, data acquisition, visualization, data preparation, model selection, fine-tuning, presentation, and system maintenance. Problem framing. This is a supervised learning, univariate regression suitable for batch learning. The project defines success, using root mean square error to quantify prediction accuracy, though mean absolute error is noted as a robust alternative if outliers are prevalent. Checklist utilization. Adhering to structured project checklists is emphasized to ensure consistency and prevent overlooking critical steps like data leakage prevention or assumption validation.
Nice.
2. Data acquisition and exploration. Sourcing data. Effective pipelines automate data fetching, decompression, and loading into pandas data frames, ensuring that environments remain reproducible and scalable. Exploratory data analysis. Analysts must use info and describe to identify data distributions, missing values, and column types. Visualizing histograms helps detect skewed distributions and capping, while scatterplots unveil geographic density patterns. Correlation analysis, the core method, helps calculate Pearson's R to identify relationships between features and the target variable. Nonlinear relationships, however, require more nuanced visualization techniques like scatter matrices. Feature engineering, creating new variables, such as rooms per household or bedroom ratios, often provides more predictive power than raw input features, significantly improving model performance. 3. Strategic data partitioning. Test set creation. Crucially, a set must be set aside before deep exploration to avoid data snooping bias, which leads to overly optimistic performance estimates. Stratified sampling, to ensure the test set represents the full population. Especially when dealing with important variables like median income, practitioners use stratified sampling based on categorical income bins to prevent sampling bias. Identifiers. When datasets are updated frequently, hashing stable identifiers rather than relying on index numbers ensures a consistent train test split. 4. Data preparation for algorithms. Data cleaning. Missing values are typically handled via imputation, where statistical metrics like the median replace nulls to preserve data integrity compared to dropping entire rows. Encoding categorical data. Text attributes like ocean proximity require transformation into numerical formats. One-hot encoding is preferred over ordinal encoding to prevent models from assuming a non-existent order among distinct categories, though it creates sparse matrices.
Okay.
Feature scaling. Algorithms are sensitive to varying scales. Standardization or min-max scaling is applied to prevent features with large ranges from dominating the training process.
Nice.
Advanced transformations. Handling heavy-tailed distributions often involves logarithmic transformations or bucketizing data into percentiles to force Gaussian-like distributions. 5. Pipelines and custom estimators. Scikit-Learn API. The framework relies on a consistent interface consisting of estimators, ensuring code modularity and readability. Transformation pipelines. The pipeline class facilitates the sequential application of data processing steps. The column transformer allows developers to apply different pipelines to specific subsets of data concurrently. Custom transformers. When built-in tools are insufficient, Creating classes inherited from base estimator transformer mixin allows for highly specific preprocessing, such as calculating geographic similarity, using RBF kernels or custom feature combinations. Production readiness. Building robust pipelines ensures that transformations applied during the training phase are exactly mirrored in the deployment environment, preventing performance degradation due to stale or improperly scaled inputs. Model training and evaluation. Initial modeling. The final stage of preparation involves fitting a baseline predictor, such as a linear regression model, using the full transformation pipeline. Performance evaluation. After training, the system is evaluated against the training set using RMC to verify the efficacy of the engineered features and chosen transformations.
Nice.
Iterative improvement. The initial model serves as a baseline, providing insights that allow the data scientist to return to the EDA or future engineering stages to refine the pipeline further. This summary outlines the essential steps for developing a robust machine learning system, emphasizing that success depends more on rigorous data preparation and well-constructed pipelines than on the selection of complex models themselves. By standardizing the workflow from data ingestion through feature engineering and evaluation, the project ensures reliability and reproducibility.
Nice. Really nice. So it's time to make a podcast on this, really. Till page number 115, I will make a podcast and listen it. Okay, 1 minute. Yes. Let me so forward tag will be better in English video. Great. It's taking time. It's okay. The music is background is good. Okay.
Have you ever wondered what goes into teaching a machine to predict?
Listen carefully. Okay? Starting with again.
Have you ever wondered what goes into teaching a machine to predict something as complex as house prices? It's not just feeding numbers into a computer. It's an intricate dance of data preparation, model selection, and constant refinement. Today, we're diving deep into an end-to-end machine learning project as described by Aurelian Jarin in his book, Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow. Chloe, can you walk us through how one even begins such a task?
Absolutely, Maggie. The first step is always to look at the big picture. This means clearly defining the business objective. For instance, if our goal is to predict house prices, we need to know how these prices will be used. Will they feed into another system, perhaps for investment decisions? Understanding this dictates how we frame the problem, what algorithms we choose, and how we measure success.
So it's not just about getting numbers, but understanding the context and impact.
Yeah.
You mentioned framing the problem. What kind of machine learning task is predicting house prices, and what implications does that have for our approach?
Predicting house prices is a classic supervised learning task because we train the model with labeled examples, meaning we have historical house prices that serve as the correct output. More specifically, it's a regression task, as we're predicting a continuous numerical value. Since we use multiple features like population, median income, and so on, it becomes a multiple regression problem. And because there's no continuous stream of new data, batch learning is suitable here, where we train the model once on all available data.
Nice.
That makes sense. Once the problem is framed, how do we measure if our model is actually doing a good job? Are there specific metrics for regression tasks?
Yes, a common metric for regression is the root mean square error, or RMSE. It tells us the typical magnitude of error our system makes in its predictions, giving higher weight to larger errors. We might also use mean absolute error, MAE, which is less sensitive to outliers. The choice depends on how critical large errors are to our business objective.
So RMSE is a good default, but MAE might be better if we have a lot of extreme price fluctuations, for example. What about assumptions? Is it important to verify what we're assuming about the data or the problem?
Crucially important. If we assume the output price is used directly, but the downstream system only cares if a house is cheap or expensive, then we should have framed it as a classification problem, not regression. Finding this out later could derail months of work, so clarifying assumptions upfront is key.
Right, so we've established the objective and metrics. Now, where do we get the data and how do we begin to interact with it?
For this project, we'd use the California housing prices dataset, which is publicly available. Duran's book uses Google Colab notebooks for hands-on work,
Making it easy to download and explore. Nice. Once downloaded, the first thing.
bedrooms has some missing values, which we need to handle.
Okay, let me read it. Okay. I think some issues there. It's not in. Once downloaded, the first thing is to take a quick look in the data structure. We use command like head to see the first rows and info to get summary of data types and check for missing values. Okay. And what kind of insight do these initial checks give us? Maggie is asking. Okay, and what kind of insights do these?
Once downloaded, the first thing is...
Let me start from here.
And what kind of insights do these initial checks give us? Are there immediate red flags or interesting observations?
Yeah.
Typically, yes. For example, in this data set, we notice that total bedrooms has some missing values, which we need to handle.
Yeah.
We also see that ocean proximity is a text attribute, so it's categorical. Histograms reveal that median income and median house value are capped, which could be a serious problem if we need accurate predictions beyond those limits. Also, many attributes have very different scales, which implies the need for feature scaling later on.
Capped values and different scales definitely sound like something to address. Before we dig deeper into exploring, Geron emphasizes creating a test set early. Why is this so critical?
Yeah.
It's to prevent data snooping bias. Our brains are excellent at pattern detection, but this also means we can subconsciously adjust our model choice based on patterns we observe in the test data. If we peak too much, our estimate of the model's performance on unseen data becomes overly optimistic. So we split off a test set, usually 20%, and put it aside.
So, an untouched final exam for the model. How do we ensure that this test set is truly representative, especially if certain features are very important like median income?
Purely random sampling can sometimes lead to a sampling bias. If, for instance, median income is crucial for house prices, we'd want to ensure our test set has a similar distribution of income categories as the full data set. This is where stratified sampling comes in. We create income categories, then sample proportionally each category to ensure representativeness. Scikit-Learn's stratified shuffle split or train test split with stratify argument handles this beautifully.
Yeah.
Once the test set is safely tucked away, we can finally explore the training data. What kind of visualizations or analyses help us gain deeper insights?
We start with geographical data. Plotting latitude and longitude as a scatter plot, perhaps varying alpha for density, reveals high-density areas like the Bay Area or Los Angeles. Overlaying house prices with color and population with circle size immediately highlights correlations. Houses near the ocean are expensive, and densely populated areas often have higher values. This visual exploration helps us spot patterns and data quirks.
That's insightful. Beyond geographical plots, what else do we look for in the data?
We look for correlations. The core method in Pandas calculates Pearson's R, showing how attributes relate. For example, median income is strongly positively correlated with median house value. A scatter matrix plot helps visualize pairwise correlations and attribute distributions. This often reveals the capping of median house value and median income, and other interesting patterns like straight lines in scatter plots, indicating data quirks that might need cleaning.
So we discover potential issues or interesting relationships. And sometimes creating new attributes from existing ones can be more revealing.
Nice.
Exactly. For instance, total rooms on its own isn't as useful as rooms per house. Similarly, bedrooms ratio, total bedrooms divided by total rooms, often correlates more strongly with house value than individual bedroom counts. Houses with a lower bedroom to room ratio tend to be more expensive. This attribute combination can significantly improve our model.
So after all this exploration, we move to preparing the data for the algorithms. What are the key steps here, and why is it important to automate them using functions?
Data preparation is crucial. It involves cleaning data, handling categorical attributes, and scaling features. Automating with functions is vital for reproducibility on new datasets, building reusable transformation libraries, and applying consistent pre-processing to test and live data, and treating these choices as hyperparameters for fine-tuning. This way, we ensure consistency and efficiency.
Let's start with cleaning. What are the options for handling missing values, like those in total bedrooms?
We have three main choices: remove the affected districts, remove the entire attribute, or impute the missing values by setting them to a statistical measure like the mean or median.
Nice.
Simple imputer in Scikit-Learn is excellent for this. It learns the median from the training data and applies it consistently across all sets.
And for text or categorical attributes like ocean proximity, how do we convert them into a format machine learning algorithms can understand?
Most algorithms prefer numbers.
Yeah.
Ordinal encoder can map categories to integers, but that implies an ordering which isn't always true. For ocean proximity, inland isn't inherently greater than near bay, so one-hot encoding is generally preferred. One-hot encoder creates a binary attribute for each category where only one is hot or 1. It outputs a sparse matrix, which is efficient for memory and computation, especially with many categories.
Nice.
So avoiding misleading ordinal relationships. Once we have numerical data, feature scaling comes next. Why is this so important?
Machine learning algorithms perform poorly when numerical attributes have vastly different scales. Imagine total rooms ranging from 6 to 39,000, while median income is 0 to 15. Without scaling, the algorithm would prioritize total rooms just because its values are larger. We use min-max scaler to scale values to a 0-1 range, or standard scaler for standardization, which results in zero mean and unit variance. Standardization is generally less affected by outliers.
And what about custom transformations? Can we integrate our own logic into this data preparation pipeline?
Absolutely. Function transformer allows us to apply custom functions, like taking the logarithm of detailed features. For more complex stateful transformations, those that learn parameters during fit, we can create custom classes inheriting from Scikit-Learn's base estimator and transformer mixin, implementing fit and transform methods. This lets us build sophisticated transformations like creating cluster similarity features.
This whole data preparation process sounds like a series of steps. How do we manage this complexity and ensure they're executed in the correct order?
Scikit-Learn's pipeline and column transformer are designed for this. A pipeline chains sequential transformations. Column transformer applies different transformations to different columns. For example, our numerical pipeline to numerical attributes, and our categorical pipeline to ocean proximity. This creates a comprehensive pre-processing pipeline, ensuring all steps are applied quickly and efficiently.
So, data prepared, what's the next step? We select and train a model?
Exactly. We start simple, perhaps with a linear regression model. We train it on our prepared data and evaluate its RMSE. With the housing dataset, a simple linear model might give an RMSE around 68,000, which isn't great, suggesting the model is underfitting. It's too simple for the data's complexity.
Underfitting is a problem. How do we know it's not overfitting? And how do we improve our evaluation beyond just one training run?
To get a more robust evaluation and check for overfitting, we use cross-validation. Scikit-Learn's cross-val score function splits the training set into multiple folds, trains the model on some, and evaluates on others. For the decision tree regressor, training RMSE might be 0, indicating perfect fit on the training data. But cross-validation often reveals a much higher RMSE, like 66,000, which is similar to the linear model. This large discrepancy between training and validation error confirms overfitting. The model memorized the training data rather than learning general patterns.
So the decision tree looks good on paper, but cross-validation reveals its flaws. What do we do after evaluating a few models? Do we just pick the best one and move on?
Not quite. The next crucial phase is fine-tuning your model. After shortlisting promising models, we optimize their hyperparameters. Grid search is a powerful technique where we define a grid of hyperparameter values, and grid search CV evaluates all possible combinations using cross-validation. For example, we might tune parameters like n clusters for our geographic features or max features for a random forest model.
So it systematically explores combinations, but what if the hyperparameter space is too large for grid search?
Randomized search is often preferred then. Instead of exhaustive evaluation, it samples a fixed number of random combinations from the hyperparameter space. This is more efficient for large search spaces, allowing us to explore more diverse values and often find good solutions faster. We can also combine models using ensemble methods, like Garden Forest, which often outperforms individual models.
Once we have the best model, how do we understand why it makes certain predictions and what insights can we gain from its errors?
We analyze the best models and their errors. For a random forest regressor, its feature importance underscore attribute tells us which features are most influential. This might show that median income is highly important, while some ocean proximity categories are less so. We can then consider dropping less useful features. Also, inspecting specific errors helps us understand why the model fails. Perhaps there are outliers or missing features that need attention, or even hidden correlations.
Finally, the moment of truth. We evaluate the system on the test set. This is the last check before deployment, right?
Yes, it is. We compute the final RMSE on the test set to get an unbiased estimate of our model's generalization error. It's crucial not to tweak the model further after this point to avoid overfitting the test set. We might also calculate a confidence interval for the error to understand its precision. Then we prepare to launch. This involves documenting everything, setting up monitoring, and regular training and backups.
That's a comprehensive overview of an end-to-end project, from setting the objective to deploying and maintaining the system. It's clear that machine learning involves much more than just coding algorithms. Transitioning from regression, let's talk about classification. Many applications today rely on classification. Chloe, how do we introduce the fundamental concepts of classification, perhaps using a well-known data set?
We often begin with the MNIT dataset, sometimes called the Hello World of Machine Learning. It's a collection of 70,000 small, handwritten digit images. Each image is labeled with the digit it represents, from 0 to 9. We use Fetch OpenML to load it from Scikit-Learn. The data itself is 70,000 images, each 28 by 28 pixels, represented as 784 features, one for each pixel's intensity. We can then visualize any digit using Matplotlib.
So, a data set of handwritten digits. How do we begin training a classifier on something like this? Do we try to identify all 10 digits at once?
To simplify, we often start with a binary classifier. Let's say we want to build a 5 detector that distinguishes between images of the digit 5 and all other digits. We create target vectors that are true for 5s and false for non-5s. A good starting point is SGD classifier, which handles large datasets efficiently and is suitable for online learning.
When we train this 5 detector, how do we measure its performance? Is accuracy a good metric here?
Interestingly, accuracy can be misleading, especially with skewed datasets where some classes are much more frequent. For MNIST, only about 10% of images are 5s. A dummy classifier that simply guesses not a 5 every time would achieve over 90% accuracy.
Yeah.
This is why accuracy isn't ideal for classifiers, and we need more robust performance measures.
That's a powerful example of why relying solely on accuracy can be deceptive. So if not accuracy, what's a better way to evaluate a classifier, especially when classes are imbalanced?
A much better way is to use a confusion matrix. It counts how many times instances of class A are classified as class B. For our 5 detector, it tells us how many non-5s were correctly identified as non-5s, true negatives, how many were wrongly classified as 5s, false positives, how many 5s were classified as non-5s, false negatives, and how many 5s were correctly identified as 5s, or true positives.
The confusion matrix offers a lot of detail. Can we condense this information into simpler metrics, and are there trade-offs involved?
Yes, from the confusion matrix, we can derive precision and recall. Precision is the accuracy of positive predictions. It tells us when the model predicts 5, how often is it correct? Recall, or sensitivity, is the ratio of positives that were correctly detected. It tells us, out of all the actual 5s, how many did the model find? The F1 score is the harmonic mean of precision and recall, useful for comparing classifiers when both metrics matter. However, there's a fundamental precision-recall trade-off. Increasing one typically decreases the other.
So we can't always have both high precision and high recall. How does this trade-off actually work in practice for a classifier like our 5 detector?
Classifier makes predictions based on a decision function score. If the score is above a certain threshold, it's classified as a 5. Raising this threshold increases precision, fewer false positives, because we're only calling something a 5 if we're very confident. But it also decreases recall, as some actual 5s might fall below the higher threshold. Conversely, lowering the threshold increases recall, but decreases precision. We can visualize this by plotting precision and recall against different threshold values using the precision recall curve function.
So we're essentially choosing how conservative or aggressive we want our classifier to be. The ROC curve is another tool for performance, but how does it differ from the precision recall curve?
The ROC curve or ROC curve plots the true positive rate, which is just another name for recall, against the false positive rate, or FPR. The FPR is the ratio of negative instances incorrectly classified as positive. A good classifier's ROC curve stays as far away from the diagonal line as possible, towards the top left corner, indicating high true positive rate and low false positive rate. The area under the curve, or AUC, quantifies this performance.
Understanding these nuances and evaluation metrics is truly essential for building reliable machine learning systems.
Okay, thank you so much. So, the podcast is over now. Now it's time to have a quiz, okay? New quiz, 20 questions, select chapters. Going to select this chapter now, chapter number 2. So till here I will select all the questions. Okay, continue and generate quiz. So the quiz is generating. So what is the smallest
Geographical unit for which the U.S. Census Bureau publishes sample data?
Smallest geographical unit? City, district, state. It's a district. Block group. Once again. Why is the RMSC generally preferred for regression performance measurement? It is more able than MAE. It gives higher weight to larger regions or less sensitive areas. Yeah. So looking at the test set early in the project. Test set will become invalid. Memory overflow. Primary risk of looking at the test set early in the project. Data snooping values. Computational data snooping bias. What does stratifying a data set aim to achieve? A test set representative of the population, faster computation of the population, higher accuracy for categorical data, faster computation of model, reduce memory, test set representative of the population, faster computation, test set representative of the population. Which method is recommended if you have missing data and want a non-destructive fix? Replacing with deleting the attribute problem. Only non-destructive fix. Imputation. Deleting is destructive. Removing the is also destructive. Random value is again imputation. Nice. What does a correlation coefficient of 1.0 imply? A strong negative correlation, a strong positive correlation. Okay. Why is it better to write custom function for data transformation? It prevents the user error. It ensures reproducibility on new data set. It is required by Python language. It is faster to type than no. It ensures reproducibility on new data sets. Why? What is one-hot encoding used for? Handling categorical attributes, converting number to text, imputing missing values, scaling continuous numerical data. Converting numbers to text. No. Handling categorical attributes, scaling continuous numerical data. Imputing missing values. Handling categorical attributes. Yeah. What is the difference between min and max scaling and standardization? Min max scaling is more affected by outliers. Min max scaling is non-linear. Standardization always requires more memory. Standardization requires restrict values to 0 and 1. Min and max scaling is more affected by outliers. Okay. And standardization is restrict values to 0 to 1. 0 and 1. This is correct. Let me select 1. Yeah. Nice. Why might you apply a log transformation to a feature? It to increase the feature's variance, to remove the feature entirely, to convert the feature into text, to shrink heavy tail distribution, to increase features variance, to shrink heavy tail distribution we use log transformation. Nice. What does a pipeline object in Scikit-Learn do? It generates new data from thin air. It increases multiple data transformation. It generates invalid data automatically. It is only used for visualization. A sequence multiple data transformation. It releases invalid data automatically. Sequences multiple data transformation. Yeah. What is the purpose of column transformer? To apply different transformation to different columns. To apply different transformation to column transformer to different columns. Yeah. What is a predictor in Scikit-Learn's API terminology? So, a class used for data visualization, an object that can make predictions, a tool for creating documentation, and an object that only performs scaling. Predictor, a class used for data visualization. An object that can make prediction. Predictor. An object that can perform scaling. Tool for creating. Class used for data visualization. No. An object that can make predictions. The predictor. What does the fit method do in a Scikit-Learn estimator? Print a summary of the model, convert text and estimate parameters from a data set. Okay. How should you handle an unknown category in production using one hot encoder? By setting under handler ignore, by using random values, by manually retraining every day, by crashing the application, by setting handler no ignore. Okay. Why is a Jupyter notebook interactivity both a benefit and a danger? It is always slower than script execution. It can lead running cell into wrong order. It forces you to use only Python. It prevents you from saving your work. Interactive but benefit and a danger. It can lead to running cell in the wrong order. This one. What is the 68, 95, 99, 99.7 rule associated with the maximum price of housing, the number of features to use, standard deviation in normal distribution, the number of rows in census, the number of features to use, standard deviation and normal distribution. 68, 95, 98, number of features no. Maximum price of housing, this can be true. Number of rows in the census. This may be correct. Yeah, fine. What does a sparse matrix store? All elements include zeros. Only non-zero elements, nothing at all, only negative elements, including zero. No. Only non-zero elements. What is the benefit of adding a custom cluster-based feature? If there's a need for scaling, it makes the data smaller. It can capture geographical similarity. Custom cluster-based feature. It can capture geographical similarity. What can you skip using a custom class for a transformer? When you can skip? Does not require training. When the transformation does not require training, then you skip custom class for this transformer. So 80% correctly is good. Block group. Thank you. It's really good. Set of representative position and an object that can make predictor and only non-zero elements. Fine. Finish quiz. Now the chapter is already over. Now I'm going to take a goodbye from you. Okay, thank you so much for watching this, and I will continue the book from this select and train a model. From here I will continue, and I will try to cover the whole chapter tomorrow. Remaining chapter I will cover tomorrow. Thank you. Okay.